Okay, so continuing what we were seeing last class, we're going to be talking about Coulomb's law. Now, Coulomb's law basically is going to be the mathematical representation of the interactions that electrically charged objects are going to have between each other, or the interactions electrically charged objects are going to have with electrical fields. And we had already seen the simulation where we had a couple of electrical charges and things that are basic that you should know. And I don't know if you guys are awake or asleep or not, but I'm going to be calling on some of you just to see if you are awake or asleep. Iskra, please. Can you and remember that when I call upon you, so please turn on your camera so I can, because I have the strip here and I don't necessarily see you. Iskra, just remind us of the laws that have to do with the signs, just the signs of the charges. We have positives and negatives, and what happens with the positives and the positives, negatives of negatives, and positives of negatives. Just refresh us on that.
Positive and positive is positive, negative negative is positive, and negative positive is negative, and positive negative is negative.
Well, let's go back a little bit. What you just mentioned are the sign rules for multiplications and mathematical operations. But if we're talking about electrical charges and forces, what did we, and some of that is in the slide here. What do we know about how those interact?
Okay, so they move outside the positive, and the other ones move inside.
That's the electrical field. And if I have two charges that are of the same sign, what's going to happen?
They're going to, I forgot the word. The word is se repelen, no?
Repel. They're going to repel each other. Perfect. And if the two charges are of different sign, what's going to happen?
They're going to attract each other.
Correct. Those are the basic rules we need to remember about the science. Thank you, Iskra. So charges that are the same are going to repel each other. Charges that are of different signs are going to attract each other. That's where the opposites attract come from. And those forces are going to be dependent on certain things. And the things you guys need to understand is that proportionality is going to be having to do with the magnitude of the charges. So if the charges are large, the force is going to be large. So it's going to be directly proportional on the magnitude, but it's going to be inversely proportional to the distance, the square of the distance. This is going to be important. It's going to be important for our discussions. The proportionality is with regards to, it is directly proportional to the magnitudes and inversely proportional to the square of the distance between. And the magnitudes of the charges, remember that the charges are going to be given in the units are the coulombs. Okay. And so that proportionality is given by a constant that we're going to call, for lack of a better word, we're going to call the electrical constant, which we're going to be calling K. We'll talk a little bit more about that later on. That proportionality is going to be given by a constant K that has a constant value. That constant K is represented by this value here, which is 1 divided by 4 pi, and a value, a parameter that's called epsilon 0. That parameter epsilon has to do with the the environment, the medium where the charges are located. If we're talking about vacuum, then it's when we refer to epsilon 0. And that has a, I don't remember if vacuum is just with 2 C's or 1, so I'm not going to write that down. That's going to be that proportionality. Epsilon is called permittivity, and that's a parameter that exists. Every medium has a certain permittivity. It's called permittivity because it's how much the medium, the environment, allows or permits the movement of electrons. Okay, so different materials are going to allow different, are going to have different permittivity, are going to allow different types or amounts of movement of electrons. Now, just to kind of visualize this, let's click on this link here. Whoops, click on this link, please, and I'm gonna put it in the chat. Click on the link and do this while I'm doing it, please. Just so you also have the simulation there. This is another simulation about Coulomb's law. Just kind of visualize what we're talking about. Let me jump over here to the screen. And you can do this at the same time. We can be talking about 2 things. This is important. I'm going to do the first one first. We're talking about bodies, things that are charged. And in the macro scale, you're going to see in the animation, let's imagine that these are things that we can see. We can touch. These are large things with regards to anything else. Atomic scale means that we're talking about very, very small things where we're not necessarily interested in the mass of these things. But let's talk about the macro scale. So click on the first one. And what we see here is that we're going to have 2 objects. Okay. Let's see. Diego. Diego, are you there?
Yes.
Diego,
Yes.
Hi, Diego. Okay, I'm going to ask you 2 questions. For charge 1, do you want it to be positive or negative?
Positive.
Let's make it positive. And give me a value between 0 and 10.
4.
4. Okay, so charge 1, thank you, Diego. I've made it a positive charge. For this visual example, for this example, the red is going to be positive, I think blue is going to be negative. So I put a charge here of 4 micro columns. Okay, this is important because the unit of columns is a small unit. Okay, so we're usually going to be working on the ranges of a micro columns, nano columns. Can somebody tell me when I use the prefix micro, what I'm talking about mathematically?
That is so small. Like
yes, but yes, I think it's Estrella. Turn on your camera, please. But mathematically, what does it mean?
Micro. That you can see it, or how?
No, mathematically. So the micro, if I'm talking, for example, if I'm talking about centimeters, it means that the centi means it's times 10 to the 3. It means it's 100. But if I'm talking about micro, what's the multiplier there? Do you remember?
Times 10 minus 6.
Minus 6. Thank you, Diego. Thank you, Stray. When we're talking about micro, and by the way, you guys, let's do a refresher on this because it's important. Okay. When we're talking about milli, it's times 10 to the how much?
To the thousandths.
Which would be
-3.
-3. It's thousands. Agreed, Ricardo, but it's to the -3. Centi is times 10 to the minus
2.
2. Good. And then for some reason we jump the units and then we go to micro. Micro is times 10 to the minus Diego already said it.
6.
6. And then we've got nano. We've got nanoparticles. Everybody talks about nanoparticles. Times 10 to the minus
9.
9. And then does somebody know what comes next? Micro, nano, and then what's smaller than nano?
Pico?
Pico. Good. And that's times 10 to the minus. There's a sequence here.
Following the
12.
order, it would be 12.
12, correct. So this is important because so we identify how small these things are. So 10 to the minus 2 means I am, let me change colors here. Tens to the minus 2 means I'm dividing by 100. Tens to the minus 3 means I'm dividing by 1,000. 10 to the minus 6 means I'm dividing by what? 100, 1,000, 10 to the minus 6, how much is that?
Million?
A million.
Millionth.
Mhm.
I remember that my professor, he would stress the importance that if you're going in the negative direction, you pronounce it like ifs at the end.
It's the nth, it's a million. So you're grabbing something and you're dividing it by a million times. And so that's the amount of zeros. And by the way, just to remember that, that's the amount of zeros you have. So if I'm to the minus 9, it's 1 and 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And to the 12, it's 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. Now, do you have a dimension as to how small that is? These are centimeters here. This is 1 centimeter. This is divided by 100. It's a meter divided by 100. Now imagine this, but with this proportion here, how small it is. Are we understanding right now how small we're talking about? Remember, when I ask you a question and your cameras are off, at least react so I know you're alive, okay? Are we good up to this point? Okay.
Yes,
Mm.
Professor.
Go ahead, Andrea, please.
What was the N that it's not nano?
This one up here?
Yes.
Oh, I'm sorry, that's my writing, Andrea, and I'm sorry about that. It's micro, it's a mu. It's actually not an N, it's this thing here. It's not, it's a mu. It's kind of like a U that instead of having the leg up here, it has it on this side. Okay, and it's called mu or micro. It's actually a Greek letter. Okay, is that clear, Andrea?
Yes,
was that
and the N is nano, right?
Nano, yep. And the P is pico. These are very small values. This is important, this refresher, because we're going to be working with very small values in this course. So in the previous courses, you could be talking of a force of kilonewtons, and you could be talking about kilo, whatever. You were talking about large things. Now we're going to be talking about small things. And so the first charge is going to be positive for microcolumns. It's going to be a very small amount, microcolumns. Okay. Now, Enya. And remember,
Yes.
please to turn on your camera so I can see you when you pop up, because I'm using the thing here and I can't see you. So Enya, are you there?
Yes.
Okay, thank you, Enya. Charge number 2. Do you want it to be positive or negative? And how many microcolumns do you want?
Negative and 2 microcolumns.
Negative, thank you. And it's going to be negative and it's going to be 2 microcolumns. Okay, good, thank you, Enya. Let's see. Juan Ignacio, you there?
Yes.
Okay, Juan Ignacio, Last, and remember, please, guys, try to turn on your cameras when you participate, just so I can see you when you pop up. And a very quick question: how far do you want these to be separated in centimeters? Within the range that's in the image.
4 centimeters.
Let's have them separated by 4 centimeters. Thank you. So I'm going to put this here in 2. And since it's 4 centimeters, the other one should be in 6. Okay. Now, what do we see up here? Can somebody tell me what we're looking at in the diagram right now? What's happening with these 2 charges? With the signs and the values we have. Anybody, or Andrea, go ahead.
Are you saying because one it's positive and one it's negative?
Yeah, but look at, yes, correct, Andrea. And also look at the information that they're showing. What does it say up there in each of the, in the image? What do you see there?
That one is going to the right and one to the left, or like with the this?
Yeah, and that means that they are trying to get together.
Track.
They're trying, and remember that we're talking about electrostatics, so these aren't moving. That's why there's these gentlemen here. That's why these gentlemen here are whole, or people. I don't know if they're gentlemen, by the way. I don't know them. I haven't met them. These people, these 2 persons are holding them. Let's imagine, Andrea, that you are this person. And choose somebody else, Andrea. Anybody?
Javier.
Javier is this person here. So first off, Andrea, you're in the negative charge, right? And you're holding it. What would you feel with regards to the force in this situation if you're holding it? Let's imagine that you're the person here holding that charge, okay? And you're holding it. And what would you feel with regards to the, what do you think you would feel with regards to the situation there?
And are you saying that it's not moving, right?
It's not moving. No, exactly. You're holding it. But what would you
But
feel?
I'm only holding it, or I'm pulling it.
No, you're holding it.
Well, nothing, because it's not moving, or
Well, let's imagine this, Andrea. Imagine this situation. You're sitting in front of me, and you're not moving, Andrea. Okay, you're not moving, and I'm sitting in front of you. Okay, and then I grab your hand. You're not moving, Andrea. You're not moving. You're the charge. But then I start moving backwards. What are you going to feel?
like tension.
Yes, you're not moving, but if I start moving, what are you going to feel? You're going to feel that you're being pulled. Would you agree with that?
Yes.
So now let's take that example over here. What's going to be happening there when you're holding the charge? And look at the image, and there are some arrows there.
That I will be like pulling the ball.
Yeah, like the charge is trying to pull you. Why? Because the charge is moving, is trying to move this way. Okay, so you would be pulling to the, you'd feel a pull towards the left. Okay, are we okay up to that point on that? Thank you.
Yeah.
Javier, now let's go over to you. Are you there, Javier? Going once?
Yeah. I'm here.
Okay,
camera
thank you,
still
Javier. Thank you, Javier. Now you're on the other side, Javier. You're on the other side. And you're holding the red, the positive charge. What would you be experiencing there?
I'm not sure if like I would feel like she's pulling towards me, like something is pulling the.
Yep.
but like
Be-
not pulling me, just like something pulling the force.
Mhm. You've got the charge here, and since these are opposites, this is going to be trying to go this way. So it's like somebody was pulling you. Now, how strong would be that pull? How strong would that pull be, Javier?
I'm not sure how to answer that question.
Well, it's written down there on the screen.
Oh, I'm not sure it was like that quite literal. 44 newtons.
It's literally for how strong would that pull be? Javier, it would be equivalent to 45 newtons. That's how strong it would feel the pull. Going back to Andrea, Andrea would feel exactly the same force, but in the but on the other side. Now, thank you, Javier. Now, how is this force calculated? It's calculated using Coulomb's law. So this 44.938 newtons is Coulomb's law. F equals K Q1 Q2 R squared, where this is Q1, this is Q2. The 4 centimeters, or rather 0.4 meters, the 4 centimeters is the distance, and K is going to be a constant that we're going to be talking about. K is actually a constant that's 9 times 10 to the 9 meters squared. No, sorry.
It's 9
Newtons.
times 10 to the 9 newtons times meter squared divided by column square.
Exactly. Thank you very much. I was forgetting where everything was. Newtons have to be on top. Meter squared, column squared. So if we do this calculation, and you can do that, we're going to get the 44 point or almost 45 newtons. What happens when I start? What happens if I change the distance? Now Andrea moves further away. What's happening with the force that you guys are going to be feeling? The force is going to go lower. So instead of it being 44 newtons, it's going to be 19. And notice that the arrow got smaller. If I move this closer, notice that the arrow starts getting larger. That means that the force is getting larger. Okay. I'm going to leave it where it was. Now, let's say that Enya changes her mind and says, no, I don't want to be -2. I want to be +2. Can somebody tell me visually? I'm trying to do this visually. Can somebody tell me visually what's happening there? And what's the difference between the previous situation? And look at the little figures. Look at the little figures. Anybody?
That they're kind of pushing.
Yeah. Why? Because what's happened now with the forces? It's the same force because I haven't changed the charges, but the charges are now the same. So what's happening with the direction of the force, or what's happening with the interaction there? Where are
It's
the
repelling.
It's repelling. Now the spheres are going to the other side. So instead of feeling a pull, what are Andrea and Javier going to be feeling? They're going to be feeling a push. Okay, because now the forces are going this way. And it's the same situation. If I go further, the force is less, but if I get closer, the force is going to be larger. And notice the figures, how the figures change. If I change the signs, the direction of the force changes, you see? Also, if I make, let's say, leave this one with a 2. If I make the other one negative, what's happening? The same situation is happening. They are repelling each other. Oh, it's 6, I'm sorry. Oh, the distance. And the distance is 4. We're going to have The original values were, oh, there we go. Now they're going to be repelling each other because they're the same. The force is going to be the same because the value of the charges are going to be the same, but the distance is the same. The force is going to be the same as in the other situations, but it's going to be opposing or it's going to be repelling. Okay, this is a visual representation of Coulomb's law. Okay, questions with this before we do some problems?
No.
Let's okay, let me jump over here to the PowerPoint again. And so similar to in Newton, there's actually the same expression applies with Newton's law or Newton's law of gravitation or gravitational force. It's the same law. Newton's gravitational force law says that the force between two bodies that have a certain mass is going to be equal to the gravitational constant times the two masses divided by the square of the distance. That force is the law that applies to bodies in space, like planets, for example. And it's very similar. It follows the same principles as Coulomb's law. We're going to be using a constant K from now on, which is the Coulomb's constant, which is 9 times 10 to the 9 Newton's meters meter squared divided by Coulomb squared, which is 1 times 4 multiplied by pi by the permittivity constant of vacuum. If we were, so unless specifically noted, all of the situations we're going to be talking about with charged particles are going to be in vacuum. Okay, are going to be in vacuum. If the charged particles were not to be in vacuum or in some other medium, then epsilon 0 would change and the constant would change. But this is the situation for vacuum. Okay. There are certain similarities between Newton's law and Coulomb's law. Oh, this note is because in the previous class, a student had made a question about this. So we can remove this first. And so both laws work with forces, but with Newton's law, we're talking about gravitational forces or large bodies or masses, and Coulomb's works with charges. Both have the inverse distance square laws, where the magnitude of the force is going to be inversely proportional to the square of the distance. Both forces apply to the center of the objects or that have either a mass or a charge. It only depends on the initial positions. It doesn't depend, the forces aren't going to change if I moved the objects around in space, as long as the distance and the magnitudes are the same, the forces are going to be the same. So what does this mean actually? It means that if I represent two charges like this, and I want to know the force between those charges that have a certain distance, it's exactly the same situation as if I were to put this charge, if I were to move this charge and put it over here with the same distance, then the force would be the same. It doesn't matter where they're located. The thing that matters are the charges and the distances. Okay. Now let's do some problems, okay? So I am going to assign some roles here, okay? I'm gonna assign some roles here. So we've got 3 houses, okay? 3 houses. So the angels turn down for what's and the Power Rangers, okay? So I'm going to ask angels, you guys are going to do calculations, okay? So you're going to do calculations. I'm not going to do any calculation. You're going to do calculations. House turned down for what's, you're also going to do calculations. And House Power Rangers, you are going to do the verification, okay? So in every problem we do, I'm going to ask, okay, House Angels, give me the value. And you're going to give me the value of the calculation. And in another problem, I'm going to ask House turn down for what's, give me the value of the calculation. And in both of those situations, I'm going to ask House Power Rangers, is the value correct or not? And you guys are going to validate that. Is that understood? Everybody?
Yes.
Okay. So have your calculators open. Okay, well, let's start with problem number 1. It says 2-point charges, QA and QB. QA is 8 microcoulomb and QB is -5 microcoulomb, are separated by a distance of 10 centimeters. What is the magnitude of the electrical force? I'm going to add something. We're gonna talk about. I need for you guys to understand magnitude and also direction, where it's going. It says the constant K is 8.988 times 10 to the 9. I don't want us to have that headache. So we're going to be using K as the rounded out constant, which is 9 times 10 to the 9. Okay. We're going to use the rounded out version of the constant. Okay. Okay, let's start off. I'm going to go over here to the whiteboard. Okay. So we have the following situation. Again, I'm going to be calling upon you guys, so you better answer. I'm not seeing the problem. So charge number 1, house angels, charge number 1. What sign and magnitude does that charge have? According to what the problem says.
QA is positive 8 and QB is -5.
Perfect. So QA is going to be positive, and it's going to be 8 microcoulombs. And then we're going to have QB is going to be negative, and it's going to be 5 microcoulombs. Okay. This is QB. And this is QA. Okay, house turned down for what's the distance between these two?
10 centimeters
10
or
centimeters.
0.1.
Perfect. Yeah, that's important. We're gonna have to do an homologize the units. So that observation is important. Diego, so it's 10 centimeters. That's actually going to be 0.1 meters. And actually these two.
Professor, it's -5. Not 5.
Oh, well, yeah, I put the sign up here. But we can add it. Yeah, but we can add it to the value here just to not generate confusion. Just that I want to note something here in the formula because I don't want you guys to get confused. But yeah, it's -5, and here the 8 microcoulombs is actually 8 times 10 to the -6. And the 5 microcolumns are going to be 5 times 10 to the minus 6 coulombs. And we are going to use Coulomb's law, okay? And for Coulomb's law says that the force that's going to be acting between these two, the magnitude of the force is going to be K multiplied by the magnitudes of the charges, which in this case would be QA and QB, divided by the square of the distance, okay? In this case, this would be the distance. Okay. So this is going to be 9 times 10 to the 9 newtons meters square coulomb squared multiplied by 8 times 10 to the minus 6 coulombs multiplied by 5 times 10 to the minus 6 coulombs divided by, whoops, 0.1 meters elevated to the square. Now, so I'm going to give you time, guys, time to do calculations. Angels, you're going to give me the calculations in a moment. Notice one thing here, and I don't know about other professors that teach these topics, and I don't know what you're going to find on the internet, but I'm going to be very specific about this. What we're calculating here is the magnitude. We do not put the signs here, okay? Because the signs are going to be misleading if we haven't established a reference frame. So we do not do the calculations with the signs, okay? Remember that. We're calculating the magnitude. We're not going to calculate the magnitude of the force with a sign, okay? So we're not going to put the signs in the calculations, okay? Angels, please give me the value of the force, the magnitude of the force.
3.6.
3.6. Something very important. 3.6 what?
Newtons.
Newtons. Okay. It's important, you guys. I'm also going to be very specific about notation and units. So we're talking about newtons. Jose Luis, please go ahead. Raise your hand. You raise your hand.
Yes. Is there a 9 over there? That's a 9?
A 9, yes. If something about my writing isn't clear, please tell me. This is this is a 9, yes.
So can I ask where did they come from?
Oh, this value here?
Yes, the 9.
This one?
Yes.
Oh, okay. Jose Luis. This is Coulomb's law. So this Coulomb's law says that the force is going to be directly proportional to the charges and inversely proportional to the square of the distance. The proportionality is given by this K, which is Coulomb's constant. Coulomb's constant is defined by this value, 9 times 10 to the 9 newtons meters squared divided by Coulomb squared. It's like, Jose Luis, if I told you, what is the value of gravity?
9.81.
And you know, how did you get that value?
Well, it's established.
It's a constant.
Yeah.
It's a physical constant that has a mathematical explanation, by the way. It's 9.8 in the metric system. It's 32 feet times squared in the other system, but it's a constant, right? This is a constant that we're gonna be using when we're talking about electrical charges. Now, there is a mathematical origin of this constant. Okay, this constant comes from a formula that says K equals 1 times 4 times pi times epsilon 0. Epsilon 0 is what's called the permittivity of vacuum. Now, what does that mean, Jose Luis? It means that these two charges are in vacuum, and vacuum has a property that's called permittivity That's a measure as to how easily charges can move in that medium. Okay?
Okay, teacher. Thank you.
If we weren't talking about vacuum, so from now on, unless specifically noted, we're always going to be using this value. Because by default, we're assuming that it's in vacuum, right? Let's assume that these charges were in, not in vacuum, that they were in a certain particular gas. Well, then we wouldn't use this constant. We would use another version of the constant, depending on the specific gas, because this one would be different. Okay, but this is a physical constant that exists that's we're going to be using. Was that clear, Jose Luis?
Yeah, teacher.
Yeah,
Thank you.
I can, oh, good, I can do it. And I'll go with you in a moment, Andrea. I wanted to give this long-winded explanation because what I didn't want to answer, Jose Luis, is it's a constant, use it. Well, yes, it is a constant and we're going to be using, but there's an origin to that constant, but it's going to be an electrical constant that's going to be a fixed value that we're going to be using when we're talking about Coulomb's law. Okay. Andrea, please go ahead.
Sir, it's because we made a mistake and it is 36.
Okay.
And my other question is that we have to ignore the constant that they are giving us on the problem. That is
Oh,
8.
I mentioned that at the beginning in the problem, Andrea. It's the thing is that the constant is actually 8.99999 times 10 to the 9. It's like pi, Andrea. If we were to be doing a calculation with pi, I could say use 3.14, but we could use 3.14, etc. What I mentioned at the beginning is for these exercises, we're going to round it up to 9 times 10 to the 9. Okay.
Yes, thank you.
Okay. So it's 36. We have to be very careful with the units. So it's 36 newtons. House Power Rangers, validate. Is that calculation correct?
Yes.
Perfect.
Yes.
Perfect. Oh, you guys, is it okay if we continue as we've done before?
Yes.
Okay. Remember, if you guys need to stretch, if you guys need to go get some water, go to the bathroom, go ahead. Okay. Lastly, before we finish up this problem, this is the magnitude of the force. And this is why I believe it's important for you guys to remember not to use the signs in the formula, because the sign is going to be depending on the reference point that I'm using. So let's say that I'm located here in this charge. I'm located here. And I want to put an arrow here that indicates to which direction that charge would be moving or is being exerted, this 36 Newton force. So house turned down for what? In what direction would this green arrow be? Right or left? And why?
Left,
We'll
because
go
we're
left.
opposite.
Negative.
It's left. So you guys are saying it would go like this. Is that correct?
Yes.
Good. House Power Rangers. Why would it be going that way?
Because opposites attract, and it just it's
Because they're opposite. They're opposites and they're trying to get together. Now let's do the same exercise over here. And this is a 36 Newton force. Now I'm on the other side. Now I'm on the other side, on the positive charge. Where would the arrow point with regards to the positive charge? Angels.
To the right.
To the right, because they're being attracted. Okay. So the direction of the force is going to depend on where I'm located, where the reference point is. Okay. So that's why I want you guys to be very careful to not put the signs here, because if I put my free body diagram here, would these 36 Newtons be positive or negative?
Negative?
Would be negative. Because I'm located here. This is my reference. But what if I put my free body diagram here?
It's
It will be
positive.
It's positive, right? So that's important, you guys. If you would have put the signs here, you would have gotten a negative value. And so just be very careful with that. So in the mathematical operation, the positive times positive, negative times negative, negative times positive, negative times positive is going to give us different signs that can be misleading, because I have to have the sign with regards to my free body diagram and the reference. Okay. Okay. Questions with this problem? Was this clear?
Yes.
Okay, good. Let's go on to the, let's go on.
Professor.
So, yes.
Can you repeat why positive?
Oh, yes, of course. Let me just do something here that I didn't do because I want to take a screenshot. This is problem. Give me a moment here. This is problem number. Okay. So I think it was who asked? I think it was
Andrea.
Andrea. Okay. So Andrea, we're clear that the magnitude is 36 newtons. That's the magnitude. That's how strong the force is. Okay. So that part's clear, right?
Yes.
Okay. We're also clear that the two charges are attracting each other. Okay. So if I position myself here on the negative one, it's going to be going that way. Well, I'm not sure where I'm pointing. It's going to be going to the left. And if I position myself in the positive one, it's going to be going to the right. Okay. Now, if I put my free body diagram in the negative charge, that means forget about the positive one. I'm looking here in the negative charge, then the force is going to the left, right, Andrea? And so if it's going to the left, the sign would be negative of the force, because in the free body diagram, the left is negative and the right is positive. Are we okay up to that point? Now that's if I put myself there. But now if I put myself in the positive charge, where is the arrow pointing? It's pointing to the right. And in the free body diagram, the right is positive. Okay, so that's why the force is positive if I'm located in the other. Okay, is that clear?
Yes.
So the sign or the direction, rather, the sign of the force is going to depend on the direction, and it's going to depend on that direction where it is with regards to the free body diagram. Okay, so that's why the free body diagrams part was very important, you guys. Okay, is that clear, Andrea?
Yes.
Okay.
Thank
Okay, good.
Ay, qué pendejo.
Oh, yeah,
Ay,
something,
perdón.
something happened there. Something
Okay.
happened. Since I don't know Spanish, I'm gonna Google the word. But I'm assuming something happened there that
I miscalculated, I'm sorry.
Don't worry, it happens. I speak to myself sometimes that way. So let's, I'm going to take a screenshot of this. So I'm gonna minimize the screen here. Give me a moment. Oh, the little Zoom strips are very, very annoying. Let me take a screenshot of this. There we go. Okay, now let's go over to problem number 2. So for problem number 2, I'm going to reuse some of this here. Give me a moment because I want to reuse, so I don't have to draw everything again. So this is going to be problem number 2. And problem number 2 says that now I've got 2 charged particles. They are different. And it's a different situation. They are 2 charges, 10 microcoulombs and 20 microcoulombs, and they're separated a distance of 10 centimeters. Okay, so I'm going to do this. Again, the Zoom thing is really annoying. Okay. House turned on for what's the value of the first charge?
It's
10.
10 microcoulombs.
10 microcoulombs. Thank you. 10 microcoulombs. 10. So this is going to be 10 as well. I'm trying to reutilize, but it's actually easier if I just erase things. Oh, and house turned on for what's that's positive, right?
Yes.
Positive. Okay. I think that should do it. Okay, it is positive. 10 microcoulombs and it's positive. And house Power Rangers, the other charge, what value and sign is that one?
Is 20 microcoulombs.
Okay, and
Positive.
what positive? Perfect. So we're going to draw it in a red here. It is positive. And it is, I think it's called QQ for some reason. It's plus 20 microcoulombs. This is 10 times 10 to the minus 6. And let's see, angels, what is the distance that separates these
10
two?
centimeters.
10 centimeters. Again, they're both 10 centimeters. Yep. And so
Professor,
yes.
is there any difference between electric force and electrostatic
Oh,
force?
good question, Leo. They're interchangeable terms. So they can be, so if we're talking about electrical force is basically any sort of interaction that can occur with an electrical field. Okay. If we want to be very specific for the situation, we say electrostatic force just to reinforce that they're not moving. Okay. Because there could be a situation where they're moving. Okay. Right now, remember that we're in electrostatic. So that's why it specifies electrostatic force, because the charges aren't moving, but they are interchangeable terms. Okay. Okay. So Let's do the calculation. So it's going to be, we're going to apply Coulomb's law here. And let's see, house turn down for watts. Please do the calculations. Give me the values here, the value of the force of the magnitude.
I got 180 newtons.
180 newtons. Okay. House Power Rangers, please validate.
Yes, I got the same.
Perfect, perfect. Thank you. Okay, so now it's 180 newtons force. This is a larger force. We're gonna do the same exercise that we did just now. Angels, is this force, is it going to be an attraction force or is it going to be a repulsion force?
Repulsion.
Repulsion, correct. So if I'm located here in the charge that's on the right, this one here, the same for you guys, house angels. If I'm located here on this charge, where would the arrow be pointing? Of the force
To the right.
to the right. Because it's a repulsion force and the force would be 180 newtons. Positive or negative if I'm located there? It got cut off. I think somebody said something, but it got cut off. Was it you, Anya?
Yes, positive.
Positive. Okay, thank you. And now if I'm located over here in the other charge, in what direction would the force be going? Left or right?
To the left.
Left.
To the left, correct. Because it's the repulsion force and it would be the same 180 newtons, but what sign would it have?
Negative.
Negative. So again, references, depending on the free body diagram, where am I located is where how the force is going to be pointing or how it's the sign or the direction. Okay. Questions with this one? It's very similar to the other one, but the signs and the magnitudes of the charges were different. Questions with this one? I'm going to take a
No.
screen. Okay, perfect. I'm going to take a screenshot. Okay, good. We're doing good. Now let's go to the next problem. Problem number 3. Now we're starting to get interested. 3 charged particles are arranged in a line, like shown in the figure. And I'm going to draw, I'm going to clear this. No, I am going to clear everything. Okay, I'm going to write down problem. Number 3. And so the charges are now organized in the following way. We've got a negative charge at the beginning. We're in a straight line. Then we've got a positive charge over here. And we've got another negative charge over here. And these are separated here by a certain distance. And they're in a straight line. These are charges A, B, and C. So how House turned down for what's? What's the value of charge A according to the problem?
-5 microcoulombs.
Okay, we've got -5 microcoulombs, and so this would be -5 times 10 to the -6 coulombs. Then we've got charge B. House Power Rangers, what is the value of charge B?
Positive 10 microcoulomb.
10 microcoulombs, thank you, perfect. And lastly, Angels, what is the value of charge C according to the problem?
-12 microcoulombs.
It's -12 microcoulombs. And there are distances here. What is the distance between A and B, Angels?
6 centimeters.
6 centimeters, and we know that that is equivalent to 0.06, right? Meters. Okay. And Power Rangers, what's the distance between B and C?
Four centimeters.
4 centimeters, and that's 0.04 meters. Okay. House turned down for what? What is the problem asking us for?
It's asking for the net electrostatic force on particle B due
Thank
to
you.
the other two charges.
Perfect, perfect. So now it gets interesting. Now there are 3 charges and there's going to be forces interacting there. But what I'm interested in is what is the force in charge B? So now we go to the free body diagrams. I'm located here. This is where I'm interested in. That's where my free body diagram is. I don't have to make it that large. This is where I'm located in charge B. So I'm located in charge B. So let's see, Angels. I'm located here in charge B. There is going to be a force. I'm going to call that force AB, which is the force between charges A and B, which is going to be, according to Coulomb's law, K multiplied by the 2 charges. I'm going to use 2 different colors here. I'm going to use 2 colors I haven't used. Let's use, why is this such a difficult decision? Let's use light blue. There's going to be a force AB between those 2 charges. That's going to be K multiplied by QA multiplied by QB divided by R AB squared. So Angels, that force AB, in what direction would that force be if I'm located here in the positive charge?
To the left.
To the left. Good and correct. The force AB would be going to the left. Now, House Angels, and I believe it was Enya that answered. Why would it be going to the left, Enya? Give us a little insight on
Because it's an attraction force to the negative.
It's an attraction force. So the thing we should be asking, if it's an attraction force and I'm located in B, where does B want to move to? It wants to go towards A. So that's why it's going in this direction. And then there's going to be another force. I'm going to draw this one in a pink. That's going to be the force between B and C. That's going to be K multiplied by QB multiplied by QC divided by the distance between B and C squared. House Power Rangers. The force BC, where would that force be going towards?
To the right.
To the right. Thank you. Perfect and correct. And I think it was Estrella that answered. Estrella, give us a little insight. Why would it be pointing to the right?
The same as Enya said, is an attraction force because it's negative. Positive and negative, it wants to attract.
Correct. So B, since it's an attraction force, B wants to go towards C. Okay. Good. Perfect. I'm gonna ask a tricky question. Which of the two forces is going to be larger?
BC.
We don't know. Let's see about that. So meaning which of the two charges is going to be wanting to pull more? I'm going to give you.
It will be BC.
Well, maybe let's do the calculations and find out. I'm going to give a weird example. Let's say that the three charges are three people. Okay. That two of the people, the blue people, person A and person C, are both attracted to person B. But B doesn't know where to go, doesn't know who to choose. But somehow A and B have different characteristics that make them attractive. And so B makes a list of these characteristics and evaluates them. And one of those two is going to win. So B is either going to go with person C or person B. What's that going to depend upon? The characteristics of each two and which one of those two convinces that person more. In this case, what are those characteristics? Were the magnitudes and the distances. So let's do the calculations. Let's see who wins out. Forces A and B. While I write this down, House Power Rangers, and let's no, I'm sorry, House turn down for watts. While I write this down, do the calculations, please, and so you can give me the value of the force times 10. So House turn down for watts. What's the value of the force AB?
125 newtons.
125 newtons. House Power Rangers, please validate. Oh, why did I repeat this? Wrote it down twice. I don't know if I did that in the previous ones. I hope I didn't.
Yes, I got 125 too.
Perfect, perfect. Thank you. By the way, I'm doing the calculations and validations thing because of the following. If you do these problems again and the calculations are wrong, don't blame me. And this is going to be 10 times 10 to the minus 6. And so angels, please do this calculations while I'm writing it down. And so you can give me the value. Wow, the wind is really crazy. I feel like the building is gonna come down. What did we get for force BC?
675.
There we go. So who's pulling the strongest here?
C.
C is pulling the strongest. C, and it's pulling a lot more than A. So person C is really attractive, intelligent, smart, witty, funny, etc. Has all of these characteristics, and so person C is winning. So person B wants to go with person C. But what the problem is asking us for is the net force. And this is where the free body diagram calculations are important. So the net force is going to be equal, looking at the free body diagram, it's going to be FBC minus FAB. And so this is going to be equal to 675 newtons minus 125 newtons, and this is going to be 550. House Power Rangers, validate my calculations. Did I do that very
Yes.
simple subtraction correctly?
Yes.
Okay. And so in the end, what's happening here is that there is going to be a net force going this way. That's going to be 550 newtons. Okay. Questions with this one? Was it clear what we're doing? Okay.
Yes.
Remember, we're not. The problems are
Yes.
going to start. The problems are going to start getting funkier. So right now we've got 3 charges. I anticipate the following. Let me take a screenshot before I scare you guys a little bit. So I need you guys to really let me know if you have questions or doubts. In the exam, eventually we're going to get there because we're going to do other examples. I might tell you there are 6 charges in the vertices of a hexagon. And I place another charge in the middle of the hexagon. What is the net resultant charge in the middle of the hexagon? Okay, which is really easy, by the way. It just sounds weird because right now we're just with 3 charges, but it's actually not that difficult. It's not that more difficult than the statics problems you used to do. Okay, so now let's go with problem number 4, which is a variation of this one, actually. Yeah, it's actually a variation of this one with different signs. So let's go with that one, and then we'll finish up. I'm going to clear this, okay? I didn't remember if I took a screenshot. Remember that all of these solutions are going to be available in the updated PowerPoint, okay? Okay, so I'm going to clear. And I'm going to go to the last problem, which is problem number 4.
Professor, I don't understand something.
Yes, let me see if I can go back here.
It's
Yeah.
about the answers of all the problems. Like we don't have any sign in the answers, like the 125 newtons or 675 and those. We just have to write them positive.
Oh, well, and that's a good question, Andrea. The net force does have a sign. The net force was 675 minus 125. It's 550. When we're writing it down here, Andrea, in these, this is the magnitude. Okay. And the magnitude doesn't have a sign. Okay. It's 125 and 620. It's how much. we put the signs when we put the magnitudes with regards to the free body diagram. Notice that the 675 was minus 125 because the other one was going on that side. And so the net force is going to have a magnitude. And it's also going to have a sign that's with regards to the free body diagram. Okay, but the electrical force is just going to be a magnitude. Okay, is that clear, Andrea?
Yes, thank you.
Okay, good. Good question, because might get a little confusing. Estrella, go ahead.
Actually, I didn't understand them.
I can.
Okay, for example, I thought that it was like something that we were going to be doing in all the problems, like the negative sign, FBC minus FB, FAB, that it was like how do you say, equation.
Well, it's not. It's actually not an. That's also a good question and observation to clear some things up. It's not necessarily an equation or a formula, Estrella.
No
It's
problem.
and the next problem is going to clear that up a little bit more. It's according to where the arrows are going. So right now, one arrow is going to the right, which is FBC, and the other arrow is going to the left, which is FAB. And so in the Cartesian plane, this is positive and this is negative. Okay. So if the force is going this way, F1, and the other force is going this way, then it's F1 minus F2. Okay. But let's say that there were three forces. Then the expression would be F1 minus plus F3 minus F2. The sign is going to be according to the direction of the force. So that's why I mentioned that when we're using Coulomb's law, what we're calculating is the magnitude. Okay. It's the value. Once we put the forces in the free body diagram, we're going to know if they're positive or negative, depending on where they're pointing. Okay.
Got it already. Thank you.
And right now we're just looking at 2 dimensions, but we're going to add some problems where there's a triangle. And so now it's in 3 dimensions, kind of like the problem we did with the bear, the bunny, and the what was it? Bear, bunny, and deer. Okay. So we're going to be looking at those problems as well. And we are going to be doing problems with a hexagon and pentagons and weird stuff like that. Let's do this one and then we'll leave. Problem number 4. I'm going to go a bit quicker on this one because we already know what we're talking about. In this case, we've got 3 charges and the 3 of them have the same sign, right? The 3 of them are positive. Okay. So the situation we have is that we've got a positive charge, we've got another positive charge, and then we've got another positive charge. The first charge is 10 microcoulombs. The second is minus 50 microcoulombs. We might not get to finish up this problem now, but if not, we'll finish it up next class. So Q1 is 10 microcoulombs. Then we've got Q2 is 50 microcoulombs. And we don't know the value of Q3. We do not know the value of Q3. What we do know is that the charges are separated by 2 centimeters. And 6 centimeters. Now, the problem is saying, what would the charge Q3 have to be? What would the charge Q3 have to be? So the total net force on charge 2 is 0. So what does this mean? We're located in Q2. And the same as the last one, we're going to have a force between charges 1 and 2. That's going to be K Q1, Q2 divided by R12 squared. And this is going to be 9 times 10 to the 9 newtons meters square column squared times 10 times 10 to the minus 6 columns times 50 times 10 to the minus 6 columns divided by 0.02 meters squared. House angels, start doing this calculation. And question to house to angels. This force 1, 2, in what direction would that force be going? Left or right?
The one in the middle or the one on the left?
We're located here and the force is between 1 and 2.
To the left. Right?
Mm,
They are attracting, no? No.
No.
To the right, sorry.
to the right, because they are both positive, so it's a
Repelling.
repulsion force. This is a different situation to the other one. These are 3 people who hate each other. These are 3 people who do not get along. So the thing is, how should Q3 be? So in the end, the person 2 doesn't care. But these are 3 people who don't like each other. Good. Do the calculation, please, here, house angels, while I do the other one. And then there's going to be a force that's going to be between 2 and 3. And that force is going to be K Q2 Q3 divided by R23 squared. And this is going to be 9 times 10 to the 9 newtons meters square column squared multiplied by 50 times 10 to the minus 6 columns. And we don't know the value of Q3. We don't know that value. That's what we're trying to find. And this is going to be divided by 0.06 meters squared.
We got
Go ahead.
11,250.
11,250 newtons. House Power Rangers, please validate.
We got the same.
Perfect, perfect. And over here, house turned down for watts. We don't know Q3, so we're going to have something multiplied by Q3, which is, and this something is this calculation here. Can you guys give me that value, please? Anybody from house turned down for watts? Give me the value of the.
It's 1,250.
1,250, and we don't know the value of, and House Power Rangers, please validate. We don't know the value of Q3. We don't know the value of Q3, so we leave it there. House Power Rangers, please validate this value here. So did we get that correctly, House Power Rangers? Before we move on.
Professor, well, I don't get that. I need to multiply 9 times 10 to the 9 times 50, right?
Times 50
Times 10 to
times
the
10 to the
minus
minus
6.
6. And then divided
divided
by 0.06 meters elevated to the
Yes,
square.
I
Jo-
got
you got a different value, Estrella? I think Jose-
125 million.
Yeah, me too.
it's in millions. I think maybe, I think Jose Miguel, you had your hand raised.
Yes, I was gonna say that.
It's 125
25 million.
and 6 zeros.
6, yeah.
Okay, it's a larger value there. And that makes sense, by the way. Okay. So that's what you guys got? Okay.
Yes.
Now, house turned down for what? That force, in what direction would that force be going?
To the left.
To the left. And why would it be going to the left? Because it's also a repulsion force. It's also a repulsion force. Okay, so this would be the free body diagram. So the net force would be F12 minus F23, which would be 1,250 newtons minus 125 million Q1. But in the end, Enya, please go ahead.
Professor, in which force do we put first when we're subtracting, or it doesn't matter for the net force?
No, it does matter, Enya. The reference is the free body diagram, Enya. So in the free body diagram, again, the free body diagram is a Cartesian plane where positive, oops, give me a moment here. Positive, positive, negative, negative. Okay, you see that, Enya? So the sign is going to be where the arrow is pointing. Okay, so you notice that that's why I'm saying F12, because where is F12? It's over here. Minus F23, because F23 is here. You see that?
Oh, okay. Thank you.
It's basically, it's going to be the right minus the left, or the top minus the bottom. Right now we're in just we're in 2 dimensions, but when we go to 3 dimensions, we're also going to have angles there. Okay, was that clear, Enya?
Yes, thank you.
Okay, perfect. And so it says that what should be the total value of the net force according to this problem? Andrea, please go ahead.
Professor, why did you put Q1 instead of Q3?
Oh, because I made a mistake, Andrea, and thank you very much for noticing that. Thank you. I made a mistake. It's Q3. My wife doesn't believe it, but I do make mistakes. Rather, she always reminds me that I do make mistakes. Thank you, Andrea. I didn't notice that. The net force should be what value?
0.
0. So, angels, can you please then give me what would the value of Q3 be then?
Sure, wait.
Okay, it would be basically the calculation of 11250 newtons divided by 125,000,000. And actually the units.
I got 9 times 10 to the minus 5.
I got it. It's there. It won't be negative when you pass the 11,250 to the right, professor.
Yes, but this is negative, so when I divide them, it would be negative times negative.
Ah, yes.
Yep.
Okay.
That's also an important observation. That's why you have to be careful with the signs, because if we would have gotten a sign for Q3 that's negative, then that would have been that would have been odd. What would can you guys give me the value?
9 times 10 to the minus 5.
Columns. Okay, that would be the value of Q3. That would be the value of Q3 to have this situation of equilibrium in the system, to make the net force 0. Which is the 9 times 10 to the minus 5 coulombs. Okay. Which I think would be would have to be around yeah, this would be 0.9. I think it would be 0.9 microcoulombs, something like that. Okay, questions with this one? I'm going to take a screenshot.
No.
Okay. What we're going to be doing on Friday is that you guys are going to be doing a workshop where you guys are going to be working on some problems, on some exercises. And we're going to do it very similar to how we worked in the math class, when we had the math class, where you guys are going to be, I've seen some problems here, and then we're going to be doing them in houses, different problems, and then reviewing them in class, and then you're going to have both materials. Okay. So any questions?
No.
Okay.
Yeah, no question.
Okay, see you guys on Friday. Have a good, yes.
I have a quick question.
Go ahead, please.
I did like a different procedure while you were doing it, so I could compare at the end.
Huh?
And I was thinking, like, if we could, I don't know how to say it.
Simplify.
Like replace. Yeah, kind of like replace all the values on the formula, because if the final force is gonna be 0, we know that the force from Q2 and Q3 is going to be the same one as 1 and 2.
Mm-hmm.
And we could like replace those values in the same formula.
Yeah, actually, yeah, there's many ways to approach this. And yeah, you can remember that I'm doing the problems in a very step-by-step way for the recordings, but yeah, we can simplify. We could actually have made these two equal. And if we did that, then this would have been eliminated, and so this would have been eliminated, and we could have done the calculation that way as well, and we would have gotten the same result. So yeah, that would have been valid, totally valid.
My question is just to know, like, if is it better this way, like, because there's less margin for error, or the other way is good?
No, the other way would have been valid as well, because you're using the same principle where you're noting that the two forces are the same. So, and you should have gotten the same result. Mm-hmm.
Yeah. Okay. Thank you.
Okay. Good. Okay. Good job, you guys. I'll see you guys on Friday. Have a good Wednesday. Bye-bye.
Thank you. Bye.
Bye.
Bye, professor. Thank you.
Bye.